Hi Algebra 2 students. This is Friday's video for Section 8.2 Day 2. And we've got the reciprocal function family, and our objective is to graph reciprocal functions and to graph translations of reciprocal functions. And I'm not sure how far we're going to get in class, so if I'm repeating some of what you already know from in class, just go ahead and fast forward through it. But we are at about this point where I'm hoping we can get through the first problem 3. Not the got it, but problem 3 in class. We'll have to see how it goes. Just in case, I'm going to cover it again here. So we can translate any reciprocal function horizontally or vertically, just as we can other functions. And we've seen this before. It's just that now it looks a little different because y equals 1 over x is our equation. And x can't be 0 because we can't divide by 0. So you're going to see here that they're talking again about vertical stretches and shrinks and any reflections. And that information comes from A. So if A is negative, then we'll have a reflection across the x-axis. So instead of being in first and third quadrants, it'll be in second and fourth quadrants when we graph it. And then if the value of A, without a negative on it, that's why we have absolute value here, if that value is greater than 1, that is a vertical stretch, just like it always has been. And if our A value, not looking at the negative, but we see that it's a fraction between 0 and 1, that's a vertical compression. So A is still doing the exact same thing it was doing, just a new location. A is on top of our fraction now. It's in the numerator. Now, translations vertically have to happen by k, but the next one we see here, they're talking about both of them. It says translation horizontal by h and vertical by k. That's the same stuff we've always talked about, because x is responsible for your right and left translations. It has to be attached to the x. But again, it's always the opposite of what we see. So if it says x minus 2, well, that means this was actually shifted 2 units to the right. And then our k value in the back, that one's normal. So if we see a plus 2 there, that means we're going to move it 2 units up. But when we're talking about the reciprocal functions, what that does is it gives us the location of our asymptotes. And like it says, x can't equal h, because if it did, then we'll be dividing by 0. So the translations a, h, and k are still there. The transformations a, h, and k are still there. So usually it is a good idea to start by graphing the asymptotes. We're going to take this off, and we're going to put, it is a good idea to start by graphing the asymptotes. That is how we graph. So in problem 3, we're graphing a translation. And as I mentioned earlier, it's quite possible that you're not needing this one and you could just fast forward through it. But again, for whatever reason, the blue from the graph didn't want to show up until I played with it a little bit. All right, so I see what is the graph of, there's my equation, and I start thinking about y equals a over x minus h plus k. And I realize that the value here that I have for h was actually negative 1 because it's x plus 1. So it's translated 1 unit to the left because h is negative 1. Now, if that's the case, that means my asymptote has also moved. And I noticed by looking at my denominator that the bad number for that would be negative 1, because 1 over negative 1 plus 1 is going to be 1 divided by 0. So my asymptote, and in this case it is a vertical asymptote, is going to be at x equals negative 1. Now, while I'm thinking about asymptotes, I see I have that negative 2 in the back. So my k value is negative 2. And if that's the case, that's my new horizontal asymptote. And that's going to be at y equals negative 2. So before I do anything else, I want to get those asymptotes on this graph. And these are, again, helper lines, so they are never solid. Never solid. Let me emphasize that because some of you have lost points in the past by putting solid lines on for those. Solid lines in math means this is my answer. That's not what these are. These are helper lines. So there are the helpers that we have. And now what I would want to do is just pick some numbers, 2 for each branch, that would get me my graph of this hyperbola. So I start thinking, what kind of x's should I pick? And I see that my axis, where my origin was at 0, 0, seems to have moved on this graph. And that's because we had to translate it 1 to the left and 2 down. So there's my new origin, and that one has a center at x equals -1. So what I want to do is pick a couple of numbers that are just to the left of that and pick a couple of numbers that are just to the right of it. So to the left would be -2 and -3. And a lot of people like to use 2 tables for these, so they have 1 branch in one table and 1 branch in the other table. So on the other side of -1, we would have 0 and 1, and then we can get some nice points. So we're going to put those back into the original equation. I'm going to put -2 in there first. So -2 plus 1 is going to give me -1. 1 divided by -1 is -1, and -1 minus 2 is -3. Then I'm going back in the original again, but this time my x value is going to be -3. -3 plus 1 is -2. So I'll have 1 over -2, which is -1/2. -1/2 minus 2 is -2.5. And let me get that graph branched. So 2 to the left and 3 down, and 3 to the left and 2.5 down. And I know that the graph is going to approach the asymptotes but never touch. So those 2 points were all I really needed to show that I know what's happening with that branch. Now let me go back up to my equation and put a 0 in for x. 0 plus 1 is 1, 1 divided by 1 is 1, and 1 minus 2 is -1. Then I'll put a 1 in. 1 plus 1 is 2, 1 divided by 2 is 1/2, 1/2 minus 2 is -1.5. And then I'll graph that branch. So 0, -1, and 1, -1.5. Again, that's all I need because I know what asymptotes are. Asymptotes are the lines that we're going to approach, but we're never going to cross. So now, we have this domain and range piece down here, and I start thinking, well, didn't I use them all? No, we didn't, because that's what the asymptotes are for. They're to say, you can't graph here. You can graph everywhere else. You just can't graph here. So my x's, I have my location of my vertical asymptote at x equals -1. So I have to say for the domain, you can't use -1. Because that vertical asymptote was there to mark and say, don't graph here. And then for the range, I have a horizontal asymptote at y equals -2. So my range needs to say, y can't be -2. Can be anything else, just can't be -2 because we cannot graph where those asymptotes are. So now we have the graph, and we've done the domain and range, and our table's only required 4 points to talk about those 2 symmetrical branches. So now, this is the point where I'm hoping we are in class, but just in case, like I said, I went ahead and did that first problem for problem number 3, just to make sure. So this one says, what is the graph of y equals 1 over x minus 4 plus 6? And I think about that generic equation, and I realize that this is going to be translated 4 units right. Because again, it looks like x minus 4, but it was actually a positive 4 that was put in there. It's opposites. So 4 units to the right is going to give me a vertical asymptote, which from now on I won't write out those words. I'll just put VA at x equals 4. So I could, if I want to, go down to the domain right now and say x can't be 4 because the vertical asymptote is there. And then my horizontal asymptote, that's the k value that's in the back. So it was translated 4 units to the right and 6 up. So that's going to be y equals 6. And my range will say, hey, use whatever you want, but you can't use 6 because that's our asymptote. So let's put those on here at x equals 4 and y equals 6. And figure out where that new origin is at. And it always depends on the x, because remember, in our tables, we're going to put in x values, and we're going to let the formula give us the y's. So our x value at that new kind of origin for our graph is going to be at 4. And I want things immediately to the left of it. 3 and 2 would do that. And immediately to the right of it to figure out what those branches are doing. And again, these numbers are going way back up there. And don't forget to add the 6. That happens sometimes when students are first graphing hyperbolas. So let's put the 3 in. And again, I'm going to do the denominator first because that has 2 terms. So you have to figure out what it is before you actually use the numerator. 3 minus 4 is negative 1. 1 divided by negative 1 is negative 1. Negative 1 plus 6 is 5. 2 minus 4 is negative 2. So 1 divided by negative 2 is negative 1/2. Negative 1/2 plus 6 is 5.5. So we have one of our branches here, and that's 3, 5, and 2, 5.5. And then let's get the other one. So we'll put a 5 in the original. 5 minus 4 is 1. 1 divided by 1 is 1. And 1 plus 6 is 7. And let's put a 6 in. 6 minus 4 is 2. 1 divided by 2 is 1/2. Plus 6 is 1.5. So we have 5, 7. And 6, 6.5. And there they are. There's our 2 symmetrical branches. So you absolutely put those asymptotes on first. Whether or not you want to wait until you're done to identify the domain and range doesn't matter at all. But you want those asymptotes on your graph first so that you don't cross them. You know, when you get to college and you're studying hyperbolic functions, if you cross a vertical asymptote, you lose lots of points. We're supposed to know that vertical asymptotes never get crossed. Alrighty, if you know the asymptotes and the value of a, you can write the equation for a reciprocal function. They're not that hard. We just have to know a, h, and k after all, and they're telling us they're going to give us a. So for problem 4, writing the equation of a transformation, this graph of a function is a translation of the graph 2 over x. So I already know that my a value is going to be 2. My job is to figure out where are the asymptotes. And let me see if I can get this one to darken up with the little blues a little bit too. Nope, so we'll just have to kind of guesstimate where we believe those are at. We're not able to see those little blue lines on there. All right, so if we had to guess, let's see. This is from 0 to negative 8. About halfway would be right there. That would be negative 4. So I'm going to say that looks about like negative 2. And then I look at all the answers and I realize, oh, no, it must have been a 3. So again, you can look at it because it's multiple choice and say, all right, so that's what they must have had there. Now I'm looking at my horizontal asymptote. Here's 0, here's 8, and I'm going to say that looks about halfway. That looks like a 4. And I look at all the answers, and yes, that's going to be a 4. They all have a form of a 3 for h, and they all have a 4 in some form for talking about our k value. Now, it needs to be up 4, so that means it has to be a plus 4. So we've already narrowed it down to this one and this one. And then what we have to do is make sure that it goes left 3. So think opposites. That's going to be an x plus 3. So left 3 is x plus 3 and plus 4, which is a. Number 4 says, oh good, you can see the little blue lines a little bit better on this one. The graph of a function is a translation of the graph of y equals 2 over x. So they're giving us that. We have to figure out the x minus h and the k in the back. What's the equation for the function? All right, well, it's a little bit better here. This looks like x equals 1, and this looks like halfway down, so x equals -4, or not x equals, y equals -4, right there. So to go 1 to the right, it should be an x minus 1. And then we have to go 4 units down. Well, down is normal. Up and down are normal, so that will be -4. So we have y equals 2 over x minus 1 minus 4. All about where those asymptotes are. You use those asymptotes for h and k. Problem 5, using a reciprocal function. The rowing club is renting a 57-passenger bus for a day trip. The cost of the bus is $750. 5 passengers will be chaperones. If the students who attend share the bus cost equally, what function models the cost per student C with respect to the number of students N who attend? And I'm going to stop right there because my first thing to figure out is, are we talking direct or inverse variation? As more people go, will they have to pay more money or less money? And they're going to pay less. The more passengers they have, the better. So the cost equals our money value there, that was $750, divided by how many students share that cost. And it did say they'd like us to use N right here for the students. So it's going to be 750 divided by how many ever people they can get to go. And that should have us thinking about the domain. What values we can put in for N. And you look up and you say 57. Oh, but remember, chaperones are free. So it's not 57 because we've got 5 passengers that have to be chaperones. So 57 minus 5 chaperones is going to be 52 people that could pay. And pretty obviously, you wouldn't want to even do this if nobody says they want to go. So we're going to need at least one person to say, yep, I'll go ahead and go on this bus trip that they have here. So there's our domain. And the next piece to this, because that was the next question, would be how many students must ride the bus to make the cost per student no more than $20? So if we make the cost 20, what would be our N value? Now we could certainly throw a 1 underneath that and cross multiply, and then divide both sides by 20. So we have 750 divided by 20. And we have 37.5, but you can't take 37.5 people. So to keep the cost no more than $20, you would have to have 38 people. Now there's another way to do this one, and that would be to go ahead and graph it, since we were talking about the domain anyway. So if we keep 750 over N, or X, as y sub 1, and 20 as y sub 2, then we can let Blinky tell us where they hit each other. So y equals, parentheses, 750 divided by X. And then we want to see when it's $20. But we have to go to the window, because remember we said that, we have to have at least one person that's willing to go and up to 52 riders. And we want that cost to be, we want it to be $20, but I'm going to put 0 to 30 so that I make sure I can see it. So there's where our branch of our hyperbola is going to hit that line, y equals 20. Second trace, number 5, get Blinky a little bit closer. Enter, enter, enter. And we should not be surprised to see that 37.5 again. So we can use a graphing calculator. When the numbers are larger, it's sometimes nice to put that in there, but then you have to make sure that you know the domain and range so that you can change those. So our answers. Here is the model. Here is the domain. and 38 people to keep that cost per student at no more than $20. The junior class is renting a laser tag facility with a capacity of 325 people. The cost for the facility is $1,200. The party must have 13 adult chaperones. All right, so 5A. Again, the more people that go, the lower the price. So the cost will be $1,200 divided by, and we can use N again to talk for the number of students there, to stand for the number of students. But once again, we have to have at least one person that's willing to go, and we can't do 325 because we have 13 chaperones. So 312. So that our domain changes based on how many chaperones we have going along. So A says if every student who attends the facility if every student who attends shares the facility cost equally, what function models the cost per student C with respect to the number of students N who attend? Right there. What's the domain of the function? Right there. How many students must attend to make the cost per student no more than $7.50? Well, let's put that in for C. And again, we could do this algebraically by cross-multiplying and then dividing by 7.5. Oops. I'll get back to the main screen. There we go. 160. 160 students. Part B. The class wants to promote the event by giving away 30 spots to students in a drawing. How does the model change? Now how many paying students must attend so the cost is no more than $7.50? Well, here's what that's going to do. That's going to change our domain, because if we're giving away 30 tickets, then we can't sell those 30 tickets. So you think, well, how is that going to change the graph here? Because the graph was C equals 120 over N. Well, the cost is going to increase. So what's going to happen is it's going to shift that cost, that hyperbola that we see, that branch, 30 units to the right. So this isn't going to be N anymore. It's now going to be N minus 30. And our domain, well, again, we lost 30 people. So they're having trouble finding people that are willing to go. And they decide we're going to go ahead and give away these 30 tickets. So now we'll take 312 and we'll subtract 30, and that'll give us 282. And let me fix my 120 was supposed to be 1,200. I found that out when I was missing a 0 up here. So let me insert that extra 0. 1,200 divided by x minus 30 over 7.5. There we go. And we can see it's been shifted to the right. Second trace, number 5. Where are you, Blinky? So Blinky was way up there. I'll bring Blinky down. Enter, enter, enter. So 190. If they can get 190 students to go or more, you know, same thing with our 160 up there. If they can get more than 160, more than 190, then they can keep that cost down to $7.50. So each one of these changed a little bit. You know, it depends on the situation. If they're going to be, well, in the first one, everybody was sharing the cost equally. But in these last two, we had situations where it's not just the chaperones, it's also those 30 tickets that they're going to give away that change the domain. And that moves our graph over to the right. So 190 students for this one. And that definitely covers our objectives for this section. We were graphing reciprocal functions and graphing translations of reciprocal functions. In fact, I would say we went a little bit above that. You know, we learned how to use the graphing calculator. So a lot of skills in 8-2, day 2. And there is the assignment. And of course, there's going to be some graphing in there as well. So after you enjoy doing your math assignment, have a great weekend.